Boyle's law is relevant to aviation, especially during the climb or descent. As the atmospheric pressure increases and decreases, air cavities in the body expand and contract, which can cause discomfort and pain. When this happens in the ear, it is called otic barotrauma, and when it occurs in the nose, stomach and teeth, it is known as aerodontalgia. Charles's law, from 1787, states that the volume of a fixed mass of gas held at a constant pressure varies directly with the absolute temperature. In other words, if a gas is heated at constant pressure, it will expand to fill a greater volume. Conversely, when a gas cools at a constant pressure, it will contract and occupy a smaller volume. This relationship lies behind the operation of the hot air balloon. The burner flame heats the air in the balloon, causing the air to expand. Because the expanded air is now less dense than the atmospheric air it replaces, the balloon rises. Dalton's law, from 1801, states that the total pressure of a gas mixture is equal to the sum of the partial pressures of the constituent gases. Dalton found that if gases of different composition were mixed, one gas did not influence another, and the total value of the mixture was the sum of the values of each gas. As you have learnt, atmospheric air comprises the mixture of gases illustrated on screen here. So Dalton's law is of interest to pilots, and we will look at this law in greater detail later. Fick's law, from 1855, states that the rate of transfer through a tissue, such as animal lung tissue, is proportional to three things. It is proportional to the area of the tissue, so the greater the area of the tissue, the greater the amount of gas that will pass through it. It is proportional to the partial pressure of the gases on either side of the tissue. Consequently, gases move from the high pressure side of the tissue to the low pressure side until there is equilibrium, when the flow will stop. And thirdly, it is inversely proportional to the thickness of the tissue. This means that more gas will pass through thin tissue than thick tissue. In the case of the lungs, oxygen is only transferred to the blood cells through the alveoli. As elsewhere in the lungs, the tissue is too thick. This law applies directly to the way that oxygen diffuses into the tissue of the lungs. The greater the area, the greater the diffusion. The thicker the tissue, the lower the diffusion. Henry's law, from 1800, states that at a constant temperature, the amount of gas dissolved in a liquid is proportional to the gas pressure. In other words, if the pressure of a gas near a liquid increases, more gas molecules will collide with the surface of the liquid and be dissolved into it. The condition in divers known as the bends is an illustration of how the law applies. As a diver descends to a greater depth, nitrogen in his body becomes dissolved under pressure into the blood. But as he rises again to the surface, the nitrogen comes out of solution as bubbles and can cause pain or even death. Similarly, a violent decompression in an aircraft at high altitude could result in similar symptoms. Opening a fizzy drink bottle and releasing some of the pressure causes gases in solution to turn into bubbles. It is another example of the application of Henry's law. Closely related to Charles's law is the law of his colleague, Gay-Lussac. He discovered that if the volume, V, of a gas is constant, K, then there is a direct relationship between pressure, P, and temperature, T. For example, if the temperature in a container is increased, the pressure increases, because the gas molecules move faster. If the temperature decreases, the pressure decreases. So, the relationship will always be the same. For example, if pressure increases from 1 to 4 units, and if temperature had an original value of 2, then the temperature would increase to 8 units. The last of the gas laws for us to look at is the combined or general gas law. This law combines Charles's law, Boyle's law, and Gay-Lussac's law. These laws each relate one thermodynamic variable to another mathematically, while holding everything else constant. You will recall that Boyle's law asserts that pressure and volume are inversely proportional to each other at fixed temperature. Charles's law states that volume and temperature are directly proportional to each other, as long as pressure is constant. Finally, Gay-Lussac's law introduces a direct proportionality between temperature and pressure, as long as it is at a constant volume. The interdependence of these variables is shown in the combined gas law, which states that the ratio between the pressure-volume constant and the temperature of a system remains constant. This is written mathematically as P times V over T equals K. Temperature in this case is measured in Kelvin. Absolute temperature is expressed in Kelvin, K, which is the temperature scale used in scientific formulae. Simply add 273 to the Celsius value to convert to absolute temperature. For example, 25 degrees Celsius is 298 Kelvin. Absolute zero, therefore, is 0 Kelvin or minus 273 degrees Celsius. You will have noticed that there is an integral relationship between temperature, pressure and volume. Decrease one and another increases, and vice versa. You are expected to know each of these laws and its relevance to aviation, but you will not be required to make any calculations. This concludes our view of the atmosphere and the gas laws.